This is just the next page. So if you want to highlight what is a trig identity? A trig identity is an equation between trig ratios that's always true. You know a couple already. Tan of theta always equals sine of theta divided by cos of theta. That was one of our big ideas. That is a trig identity you already know. Another one that you already know, sine squared theta plus cos squared theta. What does it always equal? It always equals 1. So something that always works no matter what the angle is a trig identity. You know some definitions that are trig identities. You know that cosecant theta is 1 over sine of theta. You know that secant theta is 1 over cos of theta. And you know that cotangent theta is 1 over tangent theta. So at the bottom of this page, we have these listed as reciprocal identities. Cosecant's 1 over sine, secant's 1 over cos, cotangent's 1 over tan. We also know that tan is sine over cos, and cotangent is cos over sine. And at the bottom of the page, they rearrange them a little bit. You could say that if cosecant's 1 over sine, then if I have cosecant times sine theta, it would have to be equal to 1. So what we're going to do is I'm going to give you a worksheet to start working on some identities. We're going to do a couple together. We're going to learn some of the formatting for identities, what's allowed and what's not allowed. No, someone else drew them, but I like them. So identities start off by saying prove, and if we do the very first one together, it says prove cos of t times secant of t is equal to 1. So the first thing you're going to do, you're going to take out a separate piece of paper, some loose leaf, and you're going to rewrite what you want to prove. And after you've rewritten what you want to prove, and if anybody doesn't have loose leaf, that bottom drawer there has lots of extra loose leaf. First thing you're going to do is you're going to draw a line where the equal sign is. Because we want to prove that this is true, if we work with an equal sign, we are saying we assume it's true. So we have to work separately on the left side, and some people put left side here and right side here. The right side is equal to 1. That's all we can do with that. But on the left side, we're going to have to use what we already know and change things, and then simplify fractions to see if we can make the left side and the right side exactly the same. So formatting, we rewrite what we want to prove, and we draw a line. You might want to put even right side above here and left side above there. That's fine. Draw a line to separate your left side and your right side. Then you think about the identities you already know. Can you change secant to something? What's secant equal to? Secant is 1 over cos. So that's something we already know, so we could take secant and change it to 1 over cos. And now we have multiplying fractions. What happens when I multiply, and I can change the first one to a fraction? Cos t over 1 times 1 over cos t. Are any of the factors identical? Yes. Could you see that you could simplify this and this? And what's it equal to? 1. And you have solved this puzzle. You solve the puzzle by making both the left side and the right side identical. Once you've solved the puzzle, to finish a proof, you have to formally say that the left side is equal to the right side. Therefore, does everybody know that symbol? The 3 dots? It is the most confusing symbol in the world, right? What does it mean? Therefore. But there's only 3 dots. And you say therefore. No, there should be there 3, right? No. Therefore, the left side equals the right side. And now we get fancy mathematically. Okay? I'm going to show you some fancy math stuff. When math proofs end, many textbooks at the end of a math proof write QED. That is Latin abbreviations. How good is your Latin? Pretty well? Okay. Now I'm going to pronounce this probably terribly, and all those Latin lovers out there are going to be like checking up on this and saying, okay, quod erat demonstratum, which means what was asked for was demonstrated or was shown. We were asked to prove this was true, and we did it. Okay, so this is fanciness at the end. And then, personally, I like to add my own little mark at the end of my proof. My own little mark is a little square with some fancy shading. You can add your own. If you want to do the fancy square with shading, you can. Okay? If you want to have a smiley face with a circle around it and big ears, whatever. No, once you get them, you are happy. Okay? You solve a proof, you are like, yes, it's going to happen. There's going to be some of you working in class, and you will hear someone go, yes! Like this restrained, I'm so happy I figured this one out, is going to happen. And feel free to exclaim during your proofs when you get one. Question? No, you don't have to. You can just, therefore the left side is equal to the right side. That's your statement. That has to be there. And then, yeah, I'm going to say let's put QED. Let's be formal mathematicians.
Also, what are like the possible errors for this?
If you don't write the line and you say they're equal before you've proved them, it's an automatic 1-mark deduction.
So
It's not even an E error. But the common E error is, I don't like t's. I'm going to write theta. You introduced a variable without defining it. That's an E error. I get lazy. I don't want to write, oh, off to the side I write, I know that tan is equal to sine over cos. E error. What am I missing? The theta or the t in this case. Don't be lazy. Don't forget your variables ever. One variable forgotten in one place anywhere on your page is an E3. So those are the common E errors.
So what if you have I have words that I'm throwing in equals where I shouldn't be.
If you want to write equals along the side here, and equals here to say this one is equal to that one, that's fine as long as the line is there separating. You're not equating this side to that side. Only once you've equaled them can you say that. So let's do number 10 together, just because it's a little bit more involved. Tan y cos y equals sine y. So this is what we want to prove. We rewrite it, draw our line to separate it. Now, we have choices. We can change things. We can change tan to 1 over cotangent. We can change tan to sine over cos. We can change cos to 1 over secant. We can change sine to 1 over cosecant. We have to choose something to change to. One of the strategies that we get introduced to early is, of all of our tools that we have, every single thing that we know can be changed to sine and cos. Right? If I have secant, I can change it to 1 over cos. If I have cotangent, I can change it to cos over sine. Tangent, I can change to sine over cos. So one of the key strategies we learn early is if we change everything to sine and cos, there's a good chance that we can make things look the same. So in this case, I can change tan to sine over cos. And now what do I have? Multiplying fractions. If I multiply the fractions, are any of the factors identical? Yes. So I could simplify the cos and the cos, which would mean, what am I left with? Sine. Is my left side and my right side identical? Left side, right side? Yes. Therefore, the left side equals right side. QED. Oh, nice. Done. Done. Beautiful. So what we're going to do for the last 20 minutes is we did 5 and we did 10. So you're going to finish 6, 7, 8, 9, and then keep going. And this page slowly gets more and more fraction rules and more complicated.